Now, where did we leave off in the last class? Yeah, this one. Thank you, Mia. This is her gift for me. Gift to me. Uh, where did we leave off in the last class? Colton. Okay. We talked about recurrent neural networks, and we talked about back propagation in recurrent neural networks and how you could compute a divergence, where the divergence was between sequences rather than individual vectors. And if you could compute the derivative of this divergence with respect to each of the outputs, how you could back propagate derivatives all the way from the back to the front, right? So the story so far, iterated structures are good for analyzing time series with a short dependence on the past. So these were convolutional networks or time delay neural networks, right? But if you want to analyze history all the way going back to the beginning of time, then you need recurrent structures, such as the one that we see in this figure. Now, we presented recurrent structures as a mechanism for dealing with a specific kind of data. What was that? Time series data, right? Now, suppose I told you that recurrent structures are not restricted to just analyzing time series. They can make problems simpler even in other situations. Would you believe me? Can you think of an example where having a recurrent model could make a problem orders of magnitude simpler to solve? Okay. Here's an example. If I want to create a neural network that just takes in 2 binary numbers, it's an MLP, and it must produce the answer. Now, how large is this network going to be? If I want an MLP to add 2 binary numbers, how large would this network be? 2 n-bit numbers. Anyone? Yes? Basically, addition is much like XOR, right? It's essentially just XORing. And so you're going to need, if you have a fixed number of layers, then you would end up with a network that has to be exponentially large because it has to consider every possible combination of 2 n bits. Or if you let it go deep, it's still going to be an order of n log n for adding the 2 numbers, right? But then, if I did this with recurrent, and after building such a network, if I built a network to add 2 n-bit sequences, can I use it to add 2 n plus 1 bit sequences? No, right? But then suppose I did this with recurrent networks, how large would this be? Anyone? Quentin?
Is the size constant?
Thank you, right? That's it. That's my recurrent network. It's going to take in 3 inputs, a carry bit, which would initially be 0, and the corresponding bits from each of the 2 inputs. And it's going to output the current bit and the next carry bit, right? And this is 3 inputs, 2 outputs. I think it's going to be 5 or 6 neurons, no more, tops. And this has that added advantage that the inputs can be of any length. I'm not restricted to adding only 2 n-bit numbers, right? Can you give me another problem of this kind? I can come up with any number, but I'm asking you guys to come up with something. Someone on Zoom? You guys seem to be more sharp today. Okay. How about computing the parity of a sequence? You know what the parity is. It's just counting the number of ones. If it's odd, the output is 0. If 1, if it's even, the output is 0, or vice versa. It doesn't matter. And how big would a network be if I wanted to compute the parity of a bit string? Anyone? this is, what is parity? It's XOR, right? What did we say about XORs in the second lecture? Hmm? Good God, you have forgotten the second lecture. Anybody remember? How large was an XOR network? Stella? Okay, maybe I can go to the Pokemons. Pokemon Psyduck, do you remember?
No.
Okay, let me ask 4 different Pokemons. Please go ahead. Octillery, Pokemon Octillery, do you remember?
No.
Okay, all right. One more. Blastoise, Joshna Sarva, do you remember?
It doesn't take just one neuron. It takes 3, but then Professor here at Cardinal says we could also do it in 2. What
We
is
said this
it?
is an XOR network. We said that if you had just one hidden layer, it would be exponentially sized, right? And then we also said that if you actually you were allowed to make it deep, we said it could be just order n. But nonetheless, if I built, it's going to be large. And a network that works on inputs of size n is not going to work on inputs of size n plus 1. Now, the same thing, if done with a recurrent network, is going to look like this. Where? Like this, right? It's just going to be taking the previous bit and the current bit. If both of them are the same, it outputs a 0, otherwise it outputs a 1, period, right? And that's, I think, 3 neurons. It's 2 inputs and a single output. And so you can see how something that was exponentially large and fixed in its scope, it can only work on n-bit inputs, becomes trivially small if you use recurrence. So it's not as if recurrent networks can only be used, their only function is to operate on time series. If you sort of twist the manner in which you look at problems, even standard problems can become much smaller if you use recurrence in the operations that they require, right? So here's your first problem. Five seconds, guys. Okay, Pokemon Poliwag, Aman Priyanshu, what's the answer to the first question?
I think it's false.
False, okay. And Pokemon Whismar, what's the answer to the second question?
False.
Wait. You got both wrong, man. So there are some prediction and classification problems that require very large MLPs, and a large amount of training data can be solved using small recurrent nets that require only a small amount of training data, right? So let's go back and look at the addition problem. If I'm trying to construct a network, an MLP for addition, it can be done. But how much data would I need to provide to train this network so that it never makes a mistake? Even if the network is polynomially sized, I'd have to give it an exponential amount of training data to make sure that it got every single answer right. Correct? On the other hand, if I just give it this tiny model, this is going to take maybe a couple of strings and you're done. So it's not just the size of the network, it's also the amount of training data that the network requires. This can be vastly reduced if you use the structure of the problem, for instance, to introduce recurrence. The same thing with the parity problem. For an n-bit input, to ensure that even if you have the minimally sized network, to ensure that it always gives you the right answer and never makes a mistake, you'd have to present it with every possible combination. That's going to be an exponentially sized input. On the other hand, if I do something like this, It can look at a couple of small strings. Because this has only 3 neurons, it can learn the patterns immediately, right? So once again, using the recurrent nature of the problem means that it's not only that my network becomes much smaller, the amount of training data required to learn the generalizable patterns is going to be vastly reduced. Now, as for the second one, some problems that require large, complicated convolutional neural networks and large amounts of training data could also be solved using much smaller RNNs. That's exactly what we stated. So everybody see why both of these statements are true? Right. You guys on Zoom, is that clear? Where was my problem? Okay. So here's the story so far. Recurrent structures that can be trained by minimizing the divergence between the sequence of outputs and can be trained by minimizing the divergence between the sequence of outputs and the sequence of desired outputs using gradient descent. Now, assume that you have the network. Let's try to analyze the behavior of the network, right? What was the point of recurrence? The point of recurrence, the point was that you wanted to have long-term influence of things that might have occurred a long time ago. Now, as an example, I'm going to use parsing C programs. You have open curly braces and you have closed curly braces, right? You can have these in recursed order. You can have any number. I can open a curly brace and then I can open and close any number of curly braces afterwards. And only when the very last curly brace is closed can I close the final curly brace, right? So the duration between the opening of a curly brace and the closing of a curly brace can be arbitrarily long. You'd have to hang on to that thought all the way till the end, till the program is fully done. And if your program is just required to say, is this program structurally correct? That's what your network is supposed to say. It's a simple problem. You could write a parser for it. You could write a little rule for it. Every brace that's open must be closed. That's the rule, right? A network must be able to do it. You would expect a recurrent network to also be able to do it because it just opens the brace. It's going to keep counting things and uncounting things till the last one is closed. And then if everything matches up, you're done, right? Can these networks do it? We're going to look at that, and we can look at how we can, we'll find out that it cannot, and we'll see how we can solve that problem. So let's start with this question, right? Here's my old problem. What kind of network is this? It's a convolutional network, right? Now I'm going to assume that all of the parameters of the network are bounded. If the input is bounded, so all input values are finite, can the output be unbounded? No, right? If I just analyze longer and longer inputs, if I analyze more and more of the data, can the output become unbounded? Yeah? Yeah, but this is it. The network has, it's a convolutional network, right? Guys, can this output ever be unbounded? Can I hear a loud no? Okay, louder? That's still too faint, right? You guys have to wake up. The next time I ask you this question, I expect everybody to yell. So this is what is called a bounded input, bounded output network. This network, it has bounded input, bounded output stability. It's bi-both stable, meaning if the inputs are bounded, the output is never going to blow up, right? This is the property we want. We don't want things to just blow up arbitrarily, even though your input is just fine. How about a network like this? Is this going to be bi-both stable? Yes or no? Okay. Anybody who says no, can you tell me why?
For this one, the explanation is that the sequence doesn't go on.
You can keep accumulating things, right? And if you can keep accumulating things, well, I can guarantee that it won't explode if all of my activations are bounded, say if I'm using sigmoids, but that doesn't mean that it's going to give me meaningful output. The whole thing can just saturate and can stay saturated forever, right? So it's not a very useful thing. But then analyzing nonlinear things with nonlinear activations is a bit of a challenge. So let's look at a simpler problem. What if the activations, particularly in the hidden layers, are linear? So which means that you're just computing an affine function of all of the inputs and then passing it through an identity transform and then passing it on, right? So now to find out if this network is going to blow up or not, It's sufficient to analyze the recurrent layer. We are assuming bounded inputs. So where is the accumulation happening? In the recurrent layer, right? And so you only need to analyze the behavior of the recurrent layer. And just for simplicity, I'm going to assume that there's only a single hidden recurrent layer that we need to analyze. And we're going to assume the linear activation because we know how to analyze linear activations. So this is the old streetlight effect where you look for answers where you know where you can see them, regardless of where the problem lies, right? So let's go back and look at how this thing behaves. I'm going to analyze a network where the recurrent layer, I'm speaking only of the recurrent layer, right? I'm not worried about the output layer. I'm not worried about anything underneath. Where the recurrent layer has linear activations, which means that at each neuron, recurrent neuron, you're going to be computing an affine function of the previous hidden variable and the current input. So ht equals wh, which is the recurrent weight, times ht minus 1 plus wx times xt. And the output is just the affine value itself because the linear, the activation is linear. So ht is simply zt, right? So I can just write this as ht equals, I could have just written ht right here for the recurrence. Now, let's see how this behaves. Here's what we have. I'm going to write the whole thing down. And if I have ht equals wh times ht minus 1 plus wx times xt, right? Now, what is ht minus 1? Anyone? What is ht minus 1? Can you speak louder, okay? wh of? This is ht minus 1, so plus x of xt minus 1. So I can plug this in here, correct? And what will that give me?
Wouldn't that be WH minus 1?
Pardon me?
Would that be WH minus 1?
No, wh is the recurrent weight. It's always going to be the same weight, correct? So what if I plug this in here, what is this going to be in terms of ht minus 2? W h square ht minus 2 plus wh w x xt minus 1 plus wx x t minus 2, right? But then if I, what is ht minus 2? Anyone? What is ht minus 2 using the same? This is going to be wh ht minus 3 plus wx x t minus 2. Okay. So now suppose I plug this thing here.
That would be WXXT. The left side equation. Bottom one.
Okay, thank you. Right. So if I plug that in here, what does it become? Okay, thank you, right? H t minus 3 plus WH. What's it going to be next? Help me, guys. Is it that just WH? WH squared, WX, XT minus 2 plus WH, WX, XT minus 1 plus WX, XT. Do you see a pattern? Okay, so if I took this back to the beginning of time, what is this going to become? It's going to be WH raised to
The number of times
T, right, times
H of. No, yeah, like you could do it for some value k in the middle. So.
Okay, I'll save you and me the pain because the answer is on the slide, provided I can find my clicker, which happens to have walked away. Right? So does everybody see how we expanded that, right? So without further ado, that's what it's going to look like, right? It's going to be, if I'm looking at the kth output, it's going to be, I used k instead of t over there. It's going to be wh raised to k plus 1 of h minus 1, which is the initial recurrent value. We can assume it's 0 without, for our analysis, times wh raised to k times wx times x0 plus wh raised to k minus 1 times wx times xk minus 1. You can ignore the xk generally, and you will see that the sum of this index and this index is always going to be k, right? And you're summing over all of time. So this making sense to everyone? Okay. And so where's my button? This term over here. So if I have a long input, I have my recurrence, right? I'm only looking at the recurrent layer. So this is x0, this is x1, this is x2, this is x3. If all of these were 0 and you just had x0 going in, that first term is going to be the response at time k when the input is just a single value at time 0 and nothing else, right? So I can just write that guy as the response at time k to a single input at 0, right? And so this hk over here is basically, in each case, it's the response at time k for an input at the time indicated within the parentheses. Now, is this notation making sense to everybody? Right. So the first term, so hk of x0 is at time k this value. So hk of x0 is the response if only this guy were active, the rest of it is 0. hk of x1 is the response if only this guy is active and everything from x0 and the rest on are 0. hk of x2 is the response if only this guy were active and all the rest of these were 0. Is the notation making sense? Right. And it's enough for me to analyze this one guy, right? Because you're always accumulating. If any of these blew up, this is guaranteed to blow up, right? So on the other hand, if this doesn't blow up, none of these will blow up. Because if any of them had blown up, that would have blown up. So it's enough for me to analyze this one guy. Is that making sense? If the output doesn't blow up in k minus 1 step, if the output blows, so this is the response after k minus 1 steps. This is the response after k minus 2 steps, right? So if the response has blown up after k minus 2 steps, it's definitely blown up after k steps. So that means I just need to analyze this guy to find out if there has been any blow up at any point. Is that making sense to everybody? So I will just focus on this first term and see how it behaves. So in general, I can also write the same thing for in vectors. The first term was, I was speaking in terms of scalars, but the same thing also holds for vectors. Yes?
Is our objective to find whether the weights are going up?
No, the output, you want the response of the network to blow up, right? The weights are just the weights.
Okay, so why exactly are we checking the first input then?
You're checking the output at the kth time in response to having an input at just the 0th time.
So doesn't that mean that you would want to check the output?
You're checking the last output where there's just an input at time 0.
Oh, okay.
Right? Okay. That's the response at time k when you have a single input at time 0. Okay? So we're going to analyze that. Okay? And I can write the same thing for vector systems in general. right? In vector systems, the same kind of arithmetic holds. The weights are now weight matrices. I can look at a single vector of all ones at time 0 and try to analyze how it responds. If that blows up, then everything's going to blow up, okay? Now, let's look at the scalar problem over here. If the whole thing were a scalar, if I just had, let's assume that h of minus 1, right, plus wh raised to t, wx x0 plus wh raised to t minus 1, wx x1, and so on, right? If all of the remaining guys were, if all of the rest of the inputs were 0, then all of these guys are 0. If I assume the initial h minus 1 is 0, then this is 0. And then so all you get is ht equals this one term, correct? So to analyze if the response is going to blow up or not, what do I need to consider? Which parameters determining if the output is going to blow up or not?
Just the size of W.
Just W, which W? WH, the recurrent weight, right? When will it blow up?
If it's greater than 0.
If it's greater than 0, greater than 1, it's going to blow up. If it's less than 1, it's going to diminish to 0, right? And if it's exactly 1, it's going to stay constant. You really want that thing to be. If I wanted to remember the initial value forever, what is the ideal value of WH? 1. Anything else, it's either going to blow up or it's going to go to 0. That makes sense to everybody? Okay. Make sense to you? Okay. Now, I can write the same thing for, that was for a scalar, right? I can write the same thing for vectors, just for completeness sake. In the case of vectors, it gets just a tiny bit untidier. I'm going to write ht, where ht is a vector, is simply going to be wh raised to t times x0. I'm ignoring the weight matrix for the h, for the input. This is what it will be, right? And then I can write wh using eigen decomposition. Again, wh is always going to be square, correct? Why is wh going to be square? Why is wh going to be square? Colton, why is it going to be square? What is the size of the output? What is the output? In this recursion, right, I have ht equals wh times ht minus 1 plus other terms, right? So what is the size? Are these two the same size? ht and ht minus 1, are they the same size?
Yes.
So what is the shape of wh?
Square.
Square, guaranteed square. That makes sense? You guys? So I can just analyze wh and I'm assured that this thing is square. And so I can write this as, say, u lambda, u inverse, right? I can just do an eigen decomposition of w, and it's going to be just u lambda as a diagonal matrix, u inverse. So given this, what does wh raised to k look like? What is this? Anybody?
Just like u lambda to the k and then u inverse.
U lambda to the k, u inverse.
Wait, we should
Lambda is a
change the previous thing, right? To have a u inverse instead of lambda inverse.
Pardon me?
The previous thing where you wrote down
You are
w.
correct. I am so sorry. You are right. Thank you for catching that, right? So I can write this as, where if I say lambda like so, lambda n, where the lambdas are arranged in order of decreasing value, then I can write this as lambda 1 raised to k, u, lambda, and then I can just put this matrix here, u inverse of 1, lambda 2 over lambda 1 raised to k, and so on, correct? Where the diagonals are just the fractions, because I pulled out the lambda 1 raised to k outside. Okay, for k large, what does that central thing become? As I keep increasing k, what is this going to become? Okay, let me write this more clearly. That's going to end up looking like so. I have
You mean like it's just gonna have
WH.
powers of lambdas?
So this is going to be U times U times U inverse. This is 1. All the rest of the terms are 0. This is lambda 1, lambda 2 over lambda 1 raised to k. This is going to be lambda 3 over lambda 1 raised to k, and so on. Correct? And what are those terms within the parentheses? Are they greater than 0 or less, greater than 1 or less than 1? Because lambda 1 is the largest value. As k tends to infinity, what does this become? This is simply going to become, so as for k, when k is very large, this whole thing is just going to become lambda 1 raised to k u 1 0 0 0 u inverse, right? What does this tell us? It's sufficient for me to look at the largest eigenvalue. The largest eigenvalue and the corresponding eigenvector tells me everything I need to know about how the network is going to behave. That makes sense to everybody?
Yes.
Yes or no, guys? Okay, so let's see how that actually behaves, right? For any large t, the length of the hidden vector will expand or contract only based on the largest eigenvalue. The rest can be ignored for the most part. And so if lambda max is greater than 1, this vector is going to blow up. If it's less than 1, it's going to 0. It's going to shrink, right? So what is the ideal property for your weight matrix? If you want memory forever, what is the ideal property for the weight matrix?
All your eigenvalues of magnitude 1.
All the eigenvalues must be of magnitude 1. All of them. Why? Because if you just keep the largest eigenvalue to be at magnitude 1, any input that aligns up with the remaining eigenvectors is going to vanish to 0, right? You want your entire input to stay constant, to be remembered, right? You want all eigenvalues to be of magnitude 1. So beautiful. You guys are way ahead of me, right? Here's some linear recursion. I just ran some simulations on ht equals w times ht minus 1 for a single input of all ones. On the left, you can see what happens when the largest eigenvalue is 0.9. You can see that it sort of trails down. I think, I'm not sure. There are two different lambda values. In the second case, the largest eigenvalue is one. I have two curves. One where the largest eigenvalue is 1, the other way it's slightly greater than 1, and the third is the same. So why do you think you have those little oscillations over there? And why is the response not monotonic? Absolute value, because eigenvalues can be complex, right? You're looking at the magnitude of the eigenvalues. So when you have complex things, you're going to get oscillations. Nonetheless, the magnitude is either going to blow up or it's going to vanish depending on lambda, right? So anyway, you get the idea of what's going on. Now, the thing is, we have only analyzed networks with linear activations, right? What happens if I toss in nonlinear activations? You're going to end up with much the same situation. So here, I've still taken the same recursion, except that in the recurrent layer, I have used a sigmoid activation. So I have this network where I have h of t. There's a sigmoid activation that's applied to the simple affine combination of affine function of the previous hidden state and the current input, right? So the sequences we are going to analyze are where you just have a single x0, x at time 0, and the rest of the x's are 0, right? So this is x0 is minus 0.5, x0 is 0, x0 is 0.5. Ideally, if the network were remembering your first input, you'd expect the output after a long time to to be different in the 3 cases, right? Otherwise, it means it's not remembering anything about the input. It's forgetting about the input very quickly, right? Now, I have 5 curves over here. I have 3 different sets of W. W equals 0.9, W equals 1, W equals 1.1. Within each, I have 5 curves. The 5 curves represent 5 different values of the bias B in the affine term, right? What do we observe? In all cases, is the final response after a long period of time dependent on the input? Right? If you look at the figure to the extreme right, it's identical in every case. What does this mean? It doesn't care about the input, right? What does it really care about? There is a distinction. There are 5 different curves corresponding to 5 different B's. So what is the only thing being remembered? The bias. The network doesn't care what the input is. So does this kind of recurrence satisfy the property we wanted? Not at all, right? So maybe it's my sigmoid activation. So let me try a tan H activation, right? If I see a tan H activation, look at the figures to the extreme right. Once again, if you go down any particular row, which is keeping the weights and biases constant, but only changing the initial X value, at the extreme right, are there any differences? You're going to find none. So what has happened is that if you wait long enough, eventually the input is forgotten. All the curves are different. Where it ends up is different. So where it ends up depends both on the weight and the bias. What it doesn't depend on is the original input, right? Of course, if you look at how fast the tan H forgets the input, the tan H activation forgets the input rather more slowly than the sigmoid, which is why in a recurrent network, in the recurrent layer, typically we use a tan H activation because it has the largest stable memory. Now, you can also use a ReLU. In the case of ReLU, other nasty things happen. If the input is positive and the weights are positive, it's going to blow up or it's going to just shrink. But whatever happens, it's basically not remembering the input. Nasty things happen, right? So that was with scalar recursions. I can do the same thing with vector recursion, and you're going to find pretty much the same value, same behavior. What you will find is that after a certain amount of time, what remains in the recurrent layer? If I give a single input at time 0 and no further inputs, and analyze what is stored in the recurrent layer, after a certain number of time steps, what is stored is a function of, what's it a function of? What's it going to be? Weights and biases in the which layer? Which weights and which biases? Somebody said that. The recurrent weights and biases. That's all that's going to be remembered, right? The rest of it will not matter. And now, if I use these networks to analyze a piece of code, I open a curly brace. How long is it going to be before I forget that a brace was opened? Not very long. After analyzing 2 lines of code, you've forgotten that you opened a brace. That making sense? Right? So not great behavior. And so I have this with, basically, I have several examples on the slides. But the key point is the only thing that it's going to depend on is going to be the set of eigenvalues of the weight matrices and the bias. This is regardless of the activation that you use. It's regardless of even if you do not use an activation, it's going to end up being the same. Now, there's a second aspect to this. What the first thing this told us was, unless the weight matrices have, what is the ideal property for the weight matrix? Again, somebody had mentioned this on Zoom. What was the ideal property for the weight matrix hoot hoot? Pokemon hoot hoot? That's you? Yeah. What was the ideal property? Anybody else remember? All the eigenvalues must be 1, right? Otherwise, bad things will happen. Some things will blow up, some things are going to vanish, right? But it's not just the weight matrices. If you look at these plots, the kind of response where you end up after some time also depends on a second factor, namely the activation function, right? Even if I give you a weight matrix whose eigenvalues are all 1, after a while, where you end up is going to depend on the activation function. There's one and only one activation function that does not forget. And what would that be?
Is it just linear?
The linear, something that doesn't modify the input at all. All of them are going to eventually get messed up after a few time steps in the recurrent layer. Everybody with me on that? I see some questions on faces. Any questions? Yes.
Why did we prefer the tanh?
The tanh has a longer time to forgetting. So if you look at what's happening with sigmoid, the sigmoid is forgotten in 5 steps. In tanh, there's some pattern which depends on the input, which goes on to 10 steps in this example. But after 10 steps, it's still gone. Yes. The ReLU blows up or goes down, right?
Is this the like exploding and vanishing gradient?
No, it's not, but it's related. We'll get back to that, right? So any questions so far, guys? Any questions?
Quick question. Is this similar to like stability theory and differential equations?
Fantastic, exactly. I have that on the slide, right? It's if you wanted to perform formal stability analysis, you're going to have to you're going to be considering the convergence of Lyapunov functions, look at roots criteria, pole zero analysis, and a whole bunch of other things. So we are not going through the formal theory of stability analysis, but yes, you're absolutely correct. And the behavior is much the same as unstable nonlinear control systems, right? So we have some lessons that came out of this. Firstly, bipolar activations like tanh have the best memory behavior in that they remember things for the longest amount of time. But eventually, all of the memory behavior ends up being a function of the eigenvalues of the weight matrix and the activation function. And if your if your weight matrix has non-identity eigenvalues, you're going to have crappy memory behavior. Even if it has identity eigenvalues, the mere presence of an activation function is going to make get things messed up, right? And in all cases, memory behavior is exponential. It's either going to blow up or it's going to shrink to nothing. It's the only thing that differs is how fast or how slowly it's going to blow up or shrink. Yes, Vila.
Is there any reason that people don't just use a linear activation for the recurrent structure, but keep the non-linearity only in the unmultiplied?
Lovely. You're predicting the second half of the lecture. Okay. So here's the second part. Five seconds, guys. All right. So Pokemon Shedinja, Akriti, what's the answer to the first question?
I think it'll depend on the weights and the biases, and also on the activation function we're using.
Perfect. And Pokemon Abra, Jiyun Park, what's the answer to the second question?
The first three.
Could you speak up, please?
The first three.
The first three. Does everybody agree? Right? And so, oh, what happened? Good God. I need a better clicker. And so here we are. In both cases, the first three statements are true. What is, how many time steps a recurrent network can remember something depends on the weights of the recurrent layers. it depends on the bias, it depends on the activation function. It does not depend on what you're trying to remember, correct? Similarly, what it remembers also depends on the weights, bias, and the activation function, but it doesn't depend on what you're trying to remember. Now, is that ideal behavior? Because how long you remember something must depend on what it is you're trying to remember. If I open a curly brace, then I have to hold on to it till the brace is closed, at which point I no longer need to remember it, right? Whether I want to remember something or not depends on the context. Some things maybe it's worth forgetting. Some things like an open curly brace, I have to hang on to it, but I don't have to remember it forever. Once it's closed, it's gone, right? So the memory pattern must depend on what you see in the input and not on the weights and not on the activations. It must depend on, again, if I see an open curly brace, but it's inside a comment, should I be remembering it? If I'm analyzing C code, right? So it depends on the input, what you're trying to remember, right? You have to remember, you may want to remember an open curly brace, so long as it's in a comment, that's it, right? But it's less important. So it depends on what you're trying to remember, and how long you must remember it must depend on the context and the input. What it must not depend on are the weights and the activation functions of the network, right? And so we have this fatal flaw with recurrent neural networks as they're defined in their native form. They're very sensitive to the wrong thing. They're sensitive to everything except the pattern that you're trying to remember. Now, in addition to this, so like the story so far, recurrent networks retain information on the infinite past in principle. In practice, they tend to blow up or forget. If the largest eigenvalue of the recurrent weight matrix is greater than 1, the network response may blow up. If it is less than 1, the response dies very quickly. The memory of the network depends on the parameters and the activation of the hidden units. Sigmoid activations saturate really quickly, and the network becomes unable to retain new information. ReLU activations blow up or vanish, and TANH activations are slightly more effective at storing memory, but they're still not for very long. So these are the lessons we've learned. Now, so RNNs are in principle great for time series prediction and classification, even sequence generation. They can, as we saw, simplify problems that would be much more complex if you were trying to do them with an MLP, but the memory behavior leaves a lot to be desired. Unless you're looking for very short-term memory, if you're looking for really long-term memory, recurrent networks are not it. Now, the reason we could use them for solving the XOR and the parity problems and the addition problems is that you needed a two-step memory. If you needed a 2,000-step memory, you're out of luck, right? Now, here's the other problem, and this is the problem that several of you have alluded to, which is the vanishing gradient problem. This is true for any deep network, not just recurrent network. The gradient of the error with respect to the weights and in fact the activations is unstable. How's that? So let's consider this. Consider any multi-layer perceptron with many layers, right? Now the output over here is going to be a function of these weights times the output of this layer, right? So I can say y equals fn of wn times fn minus 1. But the output of this layer, in turn, is going to be a function of these weights times the output of this layer. So wn minus 1 times fn minus 2. A network is just a giant nested function. Everybody agree, right? And so when I compute the divergence of the output of the network with respect to a desired output, I am computing a function of a function. So the divergence is also going to be just a giant nested function. So why is that important? Now, here's a vector derivative chain rule. I'm using horrible notation. I'm using the numerator denominator notation, so you'll have to pardon me for it. But then if I have something of this kind, again, the reason I'm talking about this is observe that the network output is a function of a weight times a function, right? So if I look at anything of this kind, of the derivative of a function of a weight function f of a weight w times function g of x with respect to x. So d of f of w gx over dx, I can decompose it as d of f of w gx over d of w gx times the derivative of w gx with respect to gx times the derivative of gx with respect to x. This is just your chain rule, correct? So if I represent wgx as a variable z, which is the affine variable that goes into these activation functions, then this first term is the derivative of f with respect to z, right? The second term, the g of x in the numerator and denominator go away. All that remains is w. And the third term is the derivative of g with respect to x. So are you guys comfortable with this particular thing? We've done this many times before. Is this clear to everyone? Right. The first and the third terms, what are they? They are derivatives of functions. We had a name for it. What was that? They're Jacobians, right? You have Jacobians on either side, and you have a weight matrix on the inside, okay? So when I have a deep network of this kind, and then I'm computing a final divergence of the output of the deep network, I can write the derivative of this divergence with respect to any variable inside. So remember, when you're performing back propagation, you're computing the derivatives going back with respect to the output of every layer, right? So I can pick any one of the intermediate layers or even the input as my basic variable. So x could represent anything in the middle of the layer, right? In the middle of the network. And so if I write the derivative of, if I represent the divergence as some d, it's the function d of some f of n times wn times f of n minus 1 and so on. Now, if I want the derivative of this divergence with respect to any of these f's, that's going to be the derivative of d with respect to its argument. So when I just write nabla d, it means the derivative of d with respect to everything, the term within the parentheses. Earlier, we called it wgx in the previous slide, right? Times the derivative of f with respect to its argument, right? Times wn minus 1 times the derivative of fn minus 1 with respect to its argument times wn minus. So this is the derivative of fn times wn times the derivative of fn minus 1 times wn minus 1 times the derivative of fn minus 2 times wn minus 2 and so on, all the way till you get to the variable for whom you're trying to compute the derivative, right? Is this formula making sense? Everybody, right? Now, what are the nabla terms over here? I've explicitly shown some nabla terms, inverted triangle terms. What are those? They're all Jacobians of the activations of what? The individual layers, correct? So these guys are the Jacobians of the activations for the network. In a recurrent network, these would be the Jacobians of the hidden layer, right? So now if my layer is a bunch of scalar activations, then the Jacobian matrix is going to be a diagonal matrix with only the diagonal terms being non-zero, correct? What do these things look like? Now, if I take any activation function, what is the largest value of so the derivatives, what is the upper bound of these diagonal terms? For a ReLU activation, what is the upper bound on the activations, on the derivatives? 1. For tan H, what is the upper bound on the derivatives? For a sigmoid. For a sigmoid, what's the upper bound on the derivatives? Somebody mentioned it, yeah? 0.25, right? So if you look at the derivatives of the tan H activation, shown as a curve in green, right at 0, it peaks at 1. Everywhere else, the magnitude is going to be less than 1. For a ReLU, the derivative is either going to be 0 or 1, right? For a sigmoid, the derivative is going to be 0.25 or lesser. So what this means is that my Jacobian matrix, the diagonals of my Jacobian matrix are upper bounded at 1. right? So if I multiply any vector with this Jacobian matrix, what happens to its length? Will it increase, will it decrease, or will it stay the same?
Decrease.
It will generally decrease, right? Anytime you multiply a vector by this Jacobian matrix, the length of the vector is going to decrease. Everybody with me? Right? So that means when I'm computing my derivatives going back, every time you're passing the derivative past an activation function, the length of the derivative is going to, what's going to happen to it? It's going to what? Why would it blow up? What happens when you the Jacobian is what is the upper bound on the diagonal values for the Jacobian for the scalar case? 1. So if I multiply a matrix by a vector by a matrix, diagonal matrix, whose elements are guaranteed to be 1 or lesser, what will happen to its length? Shrink, correct? So every time when you're computing the chain of derivatives going back, anytime you pass a derivative through an activation function, the derivative is going to get smaller, right? What is the other term left here that we have to worry about? What about the weights? The other term is the weights, correct? So let's look at what happens with these weights. Now, once again, the weights matrix is a matrix. What happens when you multiply a vector by a matrix? I can go ahead, tell me. So here is what happens when you multiply a vector by a matrix. I can write any matrix W as U S V transpose. This is what is this? The singular value decomposition. And what kind of matrix is this? It's a diagonal matrix where the diagonal entries are the singular values, right? And you'll have a small number of singular values which are large. And most of the singular values are going to be really small, right? Now, if I multiply any vector x with W, what do you think will happen? What do you think will happen?
Still shrinks.
So there was someone on Zoom. Can you tell me, please?
It still shrinks.
It will shrink if
it like aligns with the small singular values.
Exactly. If it aligns with the small singular values, it's going to shrink. If it aligns with the larger singular values, it's going to expand. The behavior is unpredictable. The majority of the singular values, if I have 1,000 cross, matrix with 1,000 singular values, you may have maybe 10 singular values which are large and 990 are going to be small. If I randomly pick a direction, most vectors are going to shrink, right? And the singular values are going to be either greater than 1 or less than 1. In the directions where the singular values are greater than 1, what will happen? It's going to blow up. And directions where the singular values are less than 1, it's going to shrink. But then here's the other thing. I have a sequence of vectors, correct? If I pick any vector, it may lie in the direction of a singular value that's greater than 1 for the first weight matrix. Then it gets rotated to a new position where the corresponding singular value is less than 1. So as this chain gets longer and longer, it doesn't matter which vector you begin with. The odds are eventually it's just going to shrink and die. That makes sense? Right? And so maybe it's more convenient to think of it in terms of these pairs. Each layer is going to modify the data, the derivative, by the eigenvalues or the singular values of the product of the Jacobian and the weight matrix, right? And it's going to expand in the directions where the singular value is greater than 1, and it's going to shrink in the other directions. But because each block is different from every other block, or even if they are the same, once you rotate it, you may end up you're going to almost certainly end up in a position where the singular value is less than 1. And then even if you if the length increases at one step. Further downstream, as you go down the chain, the length is going to keep shrinking. And so this is going to give us, what is it going to give us? What happens to the derivative?
You just go to 0.
It's going to keep shrinking and shrinking and shrinking. The more layers you add, it's eventually going to go to 0. Is it always going to go to 0? There are a small, eventually there is a derivative, right? What happens is that the derivatives are going to get concentrated. There will be a small number of terms, a tiny number of terms out of the millions of terms that you've got, where a small perturbation is going to make the output blow up. And the rest of them are going to have no influence at all. Is that making sense? Right. And so the gradients in the lower, earlier layers can explode in some directions. And in most directions, they're just going to vanish, right? And the problem gets worse as the depth of the network increases. So here are some examples. This is for an MNIST, 19-layer MNIST model, randomly initialized. Now remember that when you randomly initialize the network, that's when all of the derivatives are expected to be the largest. At the optimum, the derivatives are expected to be small anyway. The input is at the bottom, the output is at the top. It's a grayscale showing the magnitude of the derivative, and the all layers are the same size. So the horizontal axis shows the index of the neurons, right? And what do we see? Here, if I use the batch gradient and if I use an ELU activation, how many layers before the derivative becomes useless? 4 or 5, right? Maybe 5. This is for an ELU activation. This is for a ReLU. It's even worse, right? This is for a sigmoid. It's gone in 3. Right. So clearly, you see what is happening over here. Now, this is the batch. So this is for TANH. Same thing. It's gone in 4. Now, the ELU activation seems to be the one that's carrying the derivative for the longest, right? And that was for the batch. If I look at individual instances, you get pretty much the same behavior. In this 19-layer model, by the time you got into the 4th layer, all the derivatives are gone. And we know the math for exactly why at this point, right? This is expected behavior. This is what will happen. And of course, so, ELU activations maintain gradients longest, but in all cases, gradients effectively vanish at about 10 layers. And this is true for both batch gradients and individual gradients. And so we have this summary that recurrent networks are supposed to retain information from the infinite past, but in practice, they are poor at memorization because the hidden layers can blow up or shrink to 0 depending on the eigenvalues of the recurrent weight matrix. The memory is also a function of the activation of the hidden units. TANH is the most useful, but nonetheless, it's not great. And deep networks also, this is so the memory behavior going forward ends up being a function of the weights matrix and the activations, right? Having a weight matrix whose eigenvalues are non-identity is guaranteed to cause things to either blow up or shrink. But it also depends on the activation. Having an activation function which is not an identity activation is also going to cause you grief, right? And then going backwards, the only activation which is guaranteed not to modify the length of your vector, which one is that? The identity activation, right? Everything else is going to give you a Jacobian which does nasty things. And what about the weight matrix? What is the only weight matrix that's guaranteed not to make things blow up or shrink?
Just all eigenvalues 1.
All eigenvalues are 1, right? Unfortunately, such a network is not going to be doing anything particularly useful, right? So, and in a recurrent network, as we saw, if I just give you an input at the first time, this is just a very deep network. You're going to have exactly the same problem. Gradients are going to vanish. On the other hand, even if everything stays fine, and if you see an error after 10,000 time steps, you want to be able to trace the cause back to something that happened at the input. You want the derivatives to be able to be passed back for as long as it takes before you catch the source of the error. And this is not standard activations will not permit it, right? And so you have a situation. So, this is what we saw going forward, and we just saw what happens going backwards, right? Now, here's a problem. Time's up, guys. Pokemon Remoraid, Dongfang. What's the answer to the first question?
I think the first one is true, and the second one is true. And that's
Questions.
true. All is true.
All are true. Okay, Pokemon Magmar, Jiho Lee. Pokemon Magmar.
Here.
Yeah. Second question, what are the answers?
True.
What is true? Is the first statement true?
Yes.
Second one, the second statement true, guys? Third, fourth, also true, right? So pretty much all the statements are true. Yes.
In that matrix, is it necessary that all the values in the top part are larger than the ones in the...
Now, if I can order it, right? So it doesn't matter how you do it, I can order it.
And when you say that it aligns more with larger values, what exactly do you mean by that?
I mean, no. So this is going to have a singular, I have singular values, which are S1, S2, and so on. And then V transpose is going to be a bunch of rows, right? So this first singular value corresponds to the first vector. The second singular value corresponds to the second vector. And so anything that aligns with this vector is going to get scaled by this guy. Anything that aligns with the second vector is going to get scaled by the second guy. And so you're going to have a small number of, and all of those vectors are orthogonal. So a small number of directions will grow, the rest of them are going to shrink.
So is this somewhat like a decision boundary? Anything?
This is not a decision boundary. This is standard linear algebra, right? So, I mean,
Think of it as a line. Or...
So if I have a three-dimensional space, and if I'm rotating it with some matrix, the singular value corresponding to, say, this direction may be large, and this may be small. So if I start off with this vector, after transforming it once, the y and z components will shrink, x components will shrink, and z will get larger, and so on. Eventually, it's just going to become the z.
So that is sort of what I wanted to say, but it sort of came out from, yeah.
Okay, so anyway. So, okay, we have a problem, right? And the problem is called activation functions and weight matrices. So how can we solve it? Now remember that we want the long-term dependency, right? We want to be able to remember an open brace till you no longer need it. You don't even know how long you will need it. So if I have something like this analyzing text, Jane had a quick lunch, then the fact that I'm using the word she depends on the word Jane, which could have occurred 2 pages ago in my book, right? But then after 3 pages, I should be careful. Maybe it's not referring to Jane anymore. So all of these depends on what you're trying to remember, how long ago it was, what else you've seen in the input. And all of these have to be a function of the input and what is being remembered, and not a function of the network parameters, right? So we sort of switch to mystery and magic to solve this problem. And the mystery and magic is called the long short-term memory network. So here it is. Our problem was with weights and activations, right? So if weights are causing a problem, if weight matrices are causing a problem, what is the simplest way of solving the problem? Simply having a weight matrix is a problem, correct? So what can I do about that? Get rid of the weight matrix. But then we also found that simply having an activation function has a problem, causes a problem. So what can we do about that? Get rid of the activation function as well, right? Let's get rid of everything that's a problem. That's what we're going to do, right? On the other hand, we do want to store things in memory. And we want to store things in memory. We need to know when to store things in memory, and we need to know when to forget. Where is that information coming from? You're going to analyze the input, but also consider the context. The fact that you've seen a curly brace matters. You must remember it, open curly brace, but only if you're not in a comment section, right? And the fact that you're counting closed curly braces matters, but only if you've already got an open curly brace, otherwise it's an error, right? You're closing a curly brace, there's nothing in memory, then you're not worrying about whether to decrement the memory. You're more interested in saying something is broken, right? So there's the context you have to consider and the actual input you have to consider, and what's in memory that you have to consider. What you do not want to consider is the waits and activation. So we're going to do this. We're just going to store things in memory, and everything in memory is going to be modified based only on the input patterns and nothing else. So this gives me this network where something goes into memory and stays untouched. There are no waits. There is no activation. The only way what is in memory is going to be modified is based on analysis of the input through something called gates, which looks at the input and decides if what is an input must be memorized or not. So, but then without waits, without activations, there's nothing nonlinear happening. So we need other parts of the network. And so that is going to be done by other parts of the network. So we're just going to keep one component of the network whose only job in life is to remember things. And then we will add in more complication elsewhere to deal with how you get things into memory and how you read things from memory. So how you get things into memory is through a series of gates, which considers the current input, what's in memory, and a whole lot of other stuff. And it's going to use this information to modify what's in memory. And then what's in memory is going to be modified by other nonlinear operations before it's used elsewhere, because we do need nonlinearity in the network, right? And so that gives us this, there's a whole lot of, the gates depend on the current input, current hidden state, and any other thing that provides context, right? Including what's in the raw memory itself. So this is the long short-term memory. You explicitly latch information to prevent decay and blow up and modify it based on what you have seen in the input. The basic component of the long short-term, so this is your standard recurrent network, right? The standard recurrent network is using some combination of the input, what was previously in memory, it combines them, it puts them through a tanh activation typically. And so I'm isolating what happens at a single time instant in a block that we will call a cell. Again, I borrowed this terminology and these pictures from the web. From where? From the Cola GitHub, right? But when somebody has done a perfect job, why redo it? Now this is going to be modified to something which is far more complex looking. If you have ever seen the picture of an LSTM, it looks like this. And if you ever wondered why, it's not fallen out of the sky, right? I mean, there's a certain degree of arbitrariness to the whole process, but the basic concept remains. The basic concept is very simple. The key component is this memory structure where there are no waits and no activations. Because as we know, waits and activations cause grief going forward and going backward, right? So this is what we will call a constant error carousel. I don't know where the terminology came from, but whatever, regardless of where it came from, when you see this term, you must remember that you're really speaking of a line, which is a memory line, which has no waits and no activations. We got rid of the waits, we got rid of the activations, right? Now, so that's your constant error carousel. It carries information through. It's only affected by gate and by gates and additions. So you have gates which tell it whether it should forget things, and you have addition components which tells it whether it must increment things. You isolate the addition and incrementing and decrementing operations. So what is the first gate? A gate is a simple sigmoidal unit with outputs in the range 0 to 1. So if you multiply something in memory with 0.9, it's forgetting something, right? And it controls how much of the information is to be let through. So the very first gate determines whether to carry over history or to forget it. So there's something on in memory. You've got maybe you're counting the number of open curly braces. And now to decide whether the number of open curly braces must be decremented or not, you need a pattern detector which is looking for not open curly braces. What will it be looking for?
Context.
If I'm counting open curly braces, and if I want to decrement the memory, what must I be looking for? The closed curly braces, right? So I need a pattern detector which is looking for things that will trigger the decrement in memory. Correct? And so this means, but it's not enough to detect a closed curly brace. What else must I use as information? Whether I'm in a comment and whether I already have something in my memory, whether I'm already counting open curly braces, right? So this is a pattern detector which looks at the current input, the past state of the network, which can be obtained in many different ways. And based on these, it decides whether the what's in memory must be decremented. And this outputs a value between 0 and 1. Now, the second thing is, now I want to increment the number of curly braces, open curly braces. That's a completely different pattern detector, right? Decrementing memory required looking for closed braces. Incrementing memory required looking for open braces, right? And so for the closed curly brace, I'm actually going to be looking at a different pattern detector, which is trying to detect whether there's a closed curly brace or not, but I'll also be looking at context. Am I in a comment section or not, right? And these two together modify what's in memory in this manner. The gate, so here, the tan H detects whether there's a closed curly brace, but then there's another gate, which is a sigmoid, which decides whether this must actually modify what's in memory or not. So this first gate is called a forget gate. It's trying to decrement things, so you're forgetting things. The second gate is called an input pattern detector and an input gate. So the tan A should be detecting open curly braces, and the sigmoid decides whether this open curly brace is in a comment section or not. And if both of them say, the first one says yes and the second one says no, that's when you're going to increment what's in memory, right? And so here's how the overall operation goes. First, you forget what you need to forget based on what the forget gate found. Then you increment what you need to increment depending on what the pattern detector and the input gate found. And otherwise, the memory remains unchanged. And then subsequently, that whatever is in memory must be transformed using a nonlinear operation for actual processing. And as it turns out, in what seems to be slightly gratuitous, but maybe not, after transforming it, they like to throw in yet another gate to modify the transformed, nonlinearly transformed version of memory to scale things up or down to carry this information forward. And so, and of course, each of the gates can look not just at the nonlinearly transformed state and the input, but also what's in raw memory through what is called a peephole connection. So here's the complete set of operations. It looks very complicated when you just see the figure, but then when you look at it step by step, it's not really complicated. The logic just makes sense, right? At least it should. And here's the complete set of, I'm running out of time because there's an exam after this. So what I will do is maybe do this, what remains is just 10 minutes of lecture. I hope you guys don't mind. At 8 o'clock today evening, I'm just going to go through 10 minutes of this and wrap this up. But please do attend, all of you. Even if it's only 10 minutes, but I've been slower than normal and Linda has an exam. Okay, is time up?
Yeah,
Time's up, guys. So Pokemon Persian, can you answer?
All of them are true.
All of them are true, right? LSTMs stabilize the memory by eliminating problematic recurrent waits and activations. They update the memory based on patterns detected in the input and the current context. In the absence of external cues, they're just going to remember things forever, right? They're suited to building pattern analyzers requiring long-term memory, like code parsers. Thank you guys for your patience, and thank you also for being there today evening. I need just 5 minutes more of time, but then I've run out of time.